Hello. So I got asked how long it would take me to do the tutorial. So I reckon I didn't know offhand. So I reckon I'll just do it and then you can see how long it takes. And let's see how far we get before, yeah. So the tutorial can be found on AIC 2024. It's going to be in the links below. The tutorial assumes that you have Ngspice, Netgen, Xgam, and Magic installed. So we'll just skip the installation procedures and that's just something you can find in other videos on my channel, and there are also Docker images that other people have made where you have all the tools necessary. I haven't tried the Docker images, so anyway, let's see. Assume knowledge. Terminal, yes, I know terminal quite well. Operating system, I'm using Mac. Make project folder. Okay, let's first find somewhere to work. Okay, I'll just follow whatever I wrote. Okay, that was there already. So it's about a year since I wrote a tutorial, so that's probably why those files there. And let's try and see if we can get these things side by side. I'm gonna make the terminal a bit bigger. Something like that, maybe. And this a bit bigger. Hopefully you can see this. And then I want to make the example. Okay. Open source tools, yeah. Okay, we need a YAML file. Right, so here we just want to copy what's in the tutorial. Paste that. Okay, so what does this say? Well, I've made this small Python script called cicconf that can read these type of YAML files, and from that it can know how to name things. That's the first part, the options, and then what to download. So in this case, it downloads the CPDK. That's just borders and stuff for schematics, and it also downloads the tech. Okay. Ah, I see. I make an assumption here. So we actually have to go to tools. So let's get there, because what I have not included in the tutorial is cicconf and cicsim. I see. That's actually included in the tools, probably. Tools. So go to tools. No, that's not the one. Go all the way back. Tools. Getting started. Okay, so, okay, this is WSL stuff. I don't want that. Okay, so let's download ASEX. Let's do that here. I have all these environmental variables set up already. Now I have the tools installed. If you wanted to install the tools, then you'll follow these procedures. But what we need to do now is install cicconf and cicsim. That needs to be installed before we can run the tutorial. And that is available through ASEX. Let's just wait for this to finish. I'll pause while it's download. Okay, then we're ready. So ASX, IP, cicsim, and it wanted me to do Python the pip install. Whether it's Python or Python 3 depends on which system you're running and what your Python binary is called. For my Mac, it's Python 3, but it might be Python for you. So now it's going to install the cicsim. Cicsim is a Python script I wrote in order to run simulations. Yes, and then we need cicconf. And that's the same install procedure. It's usually the same install procedure for any Python package. And now we can just check cicsim. Yes, cicconf. Yes. Okay, let's go back to the tutorial then. Okay, so there I have my YAML file, and let's find the tutorial. Yeah, so that actually means you need to follow the tools first, even though you have Ngspice and so on. Open source tools, cxc config file. Okay, so now we clone the repo. Actually, what we're cloning now is, as I said, the borders and stuff for that, and also the technology. And now we're gonna make a new IP. So inside the technology, cicconf template, IP templates, I've made some decisions. Let's do that in what an IP should look like. So a certain format for the folder structure. So you have the design, and actually let me open Emacs so it becomes a bit more pretty. Temp, lpro, tech, and this was, what was it, cicconf, IP template, and don't worry, I'm gonna make the text a bit bigger here. Let's do 36. Hopefully that's big enough. Yes. So in the template, we have how the folder structure should look. So design, and then the IP name. Any documents that you might have, documentation like Word or Excel or whatever. The simulation and the work folder. Work is where you would start all your Xcam and Magic tools. It'll add a few files, so git ignore to ignore the most common files that you don't want in your repository. And it'll create a initial schematic. So what you're actually looking at in this part of the text is a schematic. So schematics in Xcam are actually text files, and that's quite useful because you can go in and edit them with an editor. So this is the default schematic it generates. It will generate a make file in the work directory, and that's where you can launch all the programs for running GDS, CDL, LVS, layout specific extraction, design rule check, and so on. Now that just points to a setup I've made in the tech file. So tech make, core make, and here you can actually see how all the different commands are run. So if I search for LVS, XLVS, yeah. So this is how I run the LVS. You can see it uses Magic and NetGen. Anyway, let's get back to the template. It'll make a make file for the simulation. So simulations are launched in a different directory. It also adds a default setup for Magic. So Magic will look for a .magicrc file, and it adds that to the work folder, and an xchem rc file. And for both of those, I've made sort of default setups in the tech setup that you can have a look at. It'll also add a markdown file as a README to your design. And then it will link in the technology and link in some of the default color schemes for Magic, and also the default simulation setup to ensure that you have the right transistor corners and resistors and so on. And it'll add all the necessary files to the repo, or to the local Git repo. So that is what is done when I run the cicconf new IP. So now I'll have a new folder called Ripley EX0 Sky130. So Ripley is the project name from last year. So this year it's Connor, but we're still using the Ripley for the tutorial. And here you can see, if I clear now, you can see the folder structure that has been created. Now, you have an option of adding a remote repository to this. You don't need to do that for the tutorial. I'm going to skip that. So that's if when I executed the tutorial originally and made the tutorial text, I made a tag in my Git repo for every single sort of milestone, which means that you can check out at a certain milestone and then proceed from that. We're going to skip that for now. Edit README, I'm not going to do that. You can understand how to do that. So, well, I can show you. README. And here you can edit what this is, tutorial, and so on. If you haven't used Pandoc, then it's good to know about that tool, because I can take the README and I can output the README HTML. And that makes it a bit easier to look at sort of a proper version. Actually, maybe I should do pandoc -s. Then it makes a standalone. And it looks a bit more pretty. Okay. Back to the tutorial. So what we want to do now is going to work. And if I type make here, then there's a description of what could be done. And let's actually make the current mirror. That is the task in this tutorial. Hopefully the text is still readable. Let's start there. Okay. That's a signal interface. Draw schematic. Okay. Just copy this command. And that should start XCAM. And now I'm a bit... Right. That's too bad. So for some reason, my OBS capture does not capture schematics. I wonder why. Yeah, that might make this whole video a bit pointless. Okay, because then it's gonna be hard to see what I draw. But let's do it anyway. So what did I want to do? Add transistors. Shift L. I want to go to the Sky130 library. I want to find which one? NFET 0.18 symbol, and let's add that. And I guess you can't really see it. You can't see the lines, but you can see the other stuff. I can see the lines. And let's see, I want to select the transistor by clicking on it. Let's zoom in. Bring up the options, and we want to set length 0.36 and width 3.6 and number of fingers 2. Okay. And then we want to copy it. How many do we want? We want 2, okay. Okay, and then I press W to start wiring. And I don't think you'll be able to see the wires either, but the wires will look the same as on the picture. I really like to know if you know why I can't see. Why doesn't OBS capture XCAM? We need to add ports. So there's also already some ports in here, so I'm going to just use those. So to add a port, you go into the Schematic library IPin, for example, and that's an input pin. So what did I want to call that? I wanted to call that IBPS for micro. I'm pressing M now to move and connecting it up, which you can't see. Oh, that's horrible. And then we want an output port. So now I press Shift I. So we want an open. And I see that actually in the picture my M1 and M2 are swapped. So I'm going to flip those. Doesn't really matter, but let's make it the same as in the tutorial. What else was I supposed to do here? Yeah, save the schematic, that's important. Okay, so now we want to netlist it. We go back to the work folder, make XCH. So a good thing to know is that make XCH automatically picks up the cell name. So if you look inside the make file, you have the cell name here. If I wanted to netlist a different design, I could write, for example, cell Ripley XO EN1 if I had that schematic. And XCAM apparently doesn't really care if you give it a schematic that doesn't exist. So it actually creates an empty schematic then for the last one, I think. That's good to know that it'll actually netlist even an empty thing. Okay. So let's look at the first schematic. So that was EX0. And actually, let's do that with syntax highlighting. So we want to go to work, XCH, that one, and just do spice mode. Okay, so here we can see we have 2 transistors. And wait a minute, it looks like I may have forgotten to connect something or name something. Yes, I did. So this was IBNS 20 microamps. Let's save that. And then Netlist again. Let's go back to Emacs. Okay, so now we have drain, gate, source. Drain, gate, source. That looks correct. And then we have 2 transistors that are, well, it's not that easy to see the width, I guess. So it's in there somewhere. Ah, there we go. L36, L36, W3x6. Okay, good. Now we want to set up a simulation. So I want to go to the sim folder. And you notice that cicconf will have created a makefile in the sim folder also. And if you have a look at what's inside this make folder that is linked in, it is actually the command that you see on the screen here. So here you can copy this one. So replay EX0 Sky130, that's a library, and then that's a cell. When you run that, it will create a simulation folder. So let's go into the simulation folder and have a look at what's there. It creates a default setup for a transient simulation. So it contains a makefile. And let's look at the content of that makefile. Sim. Probably need a slightly smaller font. Hopefully, let's keep it a big font so it's easier to see for you guys. So, the makefile is where you launch simulations. It has the commands in order to Netlist, and it has the command in order to simulate. So if I write make typical, it will simulate the design using cicsim. So cicsim is not the simulator. cicsim is just a way to orchestrate simulations. So underneath, it'll run Ngspice. And there's the description of the different files. I would recommend that you have a look at those. But we can just run a simulation now. Make typical. And then that will run the transient.spy test bench. Well, that's weird. It shouldn't take that long. Oh, right. Yes. I know where it takes long. I did a modification in my later designs where I changed the CIC YAML file. So actually, let's maybe have a look at this. All these different things that is run in the makefile or added in the makefile, these GT, ATT, TT, VT, and so on, that is actually referring to lines that are in the YAML file here. And this defines what is included in the Spice file. And particularly for corners, here it includes the default setup for for the Sky130. Now, turns out the default setup for Sky130 reads an huge amount of Spice files. It's about 48 megs or something. And in later versions, I have changed what this corners are named. And just be aware that if you're using the latest version of the tech library, it will have changed. So it might not be ATT anymore, it may be KTT or something like that. But it'll run faster. Anyway, we can see this simulation ran now. So let's go to where would I want to go? Here, simulation, and let's look at the tran.spy. So the default tran.spy file that will include a VDD. That's actually not used. We didn't have a VDD on our circuit because we only had VSS, IBPS 4, and IBPS 20 micro. So what we want to do now is add a current and also add a force on the diode on the output, so we can actually measure the current. And then we want to modify the measurements. So when you're running Ngspice simulations, it's a very good idea to split up the actual simulation and what we call the measurements, or the extracting the parameters. And I've done that by splitting into two files. I have the test bench, the tran.spy, and then there will be a tran.mess in this folder. And here is where cicsim comes in, because first it will run tran.spy, and then if it finds a tran.mess, it'll run that afterwards. But the neat thing is I can tell cicsim not to rerun the simulation if I haven't changed the design. So for example, if I run make typical and I add an option of no run, then it'll now run the simulation, but it won't run the simulation, but it'll try to run the extraction. However, I added now the V0 and IBP in the test bench, so actually in this case I need to rerun the simulation. Make typical. Yeah, and it actually says here in the tutorial that you can run again. Let's see, it still fails. So it's called V0. IBN IV0. Oh, I think maybe, yes. I've forgotten to save. So we want we want the current of V0. That needs to be saved. So in Ngspice, or in Ngspice, you have to tell it which nodes it should save, and you should get into a habit of only saving what you need, because otherwise the simulation files will become very, very large if you save everything, and the simulation will also become slow. So strongly recommend that you only save what you need. I've forgotten how incredibly long. Well, still not working. Okay, then we need to look at the results. So if I open a new terminal and loads output tran raw. Okay, so here I can see I only have VBNS, IBPS. I did not, so for some, oh, I wrote it wrong. This is V0, this is VO. Okay, try again. And here it says save the current by adding IVO to the save statement in the test bench. Read the RTFM. Yeah. But this will happen when you read a tutorial and then do stuff, and things will not work. One part might be due to read the fucking manual, but the other part might be due to there's an error in the manual. Right. Okay. Now we're getting somewhere. So first of all, we can see that our current IBN is 20 microamp. It is not 20 microamp. It is 4 microamps ish. It's a bit more than 4, and that's kind of to be expected, since in our current mirror now we can see that the VGS M1, so that's the VGS of M1 in the figure, that is 0.65, and I put in 1 volt on the IBNS, which means that that voltage is higher. As such, there is some channel length modulation here that increases my current. It's not exactly 4. Actually, let's do that because that's fun to do. So if I put in exactly the same number, 0.6596729. So that's now my voltage on the right side of the current mirror is exactly the same as on the left side. If I now rerun the simulation, I should see exactly 4 microamps. So crossing fingers. If the world is correct, I should see exactly 4 microamp. Let's see. Yeah, that's pretty close to 4 microamp. So that's why the currents are different. Now, we want a 20 microamp, which means I need to increase the size of my current mirror. And as it says in the tutorial, you can add a label on the M2 device. And now make sure that you have that the M2 is the one at the output of 420. Save that. And I can make typical again. And while I do that, so cicsim also supports extracting results. In order to know what to extract from the measurements and sort of present in a decent manner, it has to know what and what to compare to. So that's what's in the tran.yaml file. There will be, for example, for the current, I tell it which measurement it should look for, just a description of what that is, and what kind of specification do I want. So do I want plus minus 20%, for example, on the current? Maybe I'm happy with that. What number to multiply with, how many digits to show, what the unit should be, and the same for the gate source voltage. So yes, the simulation is finished, and now we can see the currents closer to 20 microamps. And before and then let's just rerun, because now it will discover information in the YAML file, and it'll actually extract these 2 parameters. So check waveforms. Yeah, okay, good. So that's actually what I did in this terminal. But let's go out here. We can there's a couple of different ways of looking at waveforms. So we can use Ngspice built-in editor. I can load the output tran and the raw file that is written. And I can plot the IBPS 4 microamp to see how, as a function of time, that current evolves. And here you can see it reaches so in the beginning, it'll start out at a low value. This is just the operating point that I found based on some sort of transient operating point, or an initial guess of what the value should be, and then we can see it settling to the final value. And if we look at the current, we will see a similar phenomena. That the current settles to a final value. Okay, so Ngspice has the built-in editor. I wouldn't say it's the greatest, but at the same time, maybe there is no greatest. But what I have done in the latest cicsim is to make one. So it's also possible to use cicsim wave. Now cicsim wave requires that you have Python TK installed. But now you can see you can sort of just plot the voltage directly here, and yeah, I can I add a new plot? Yeah, I can add a new plot and then plot the current. And here it's a bit easier because this is matplotlib, so I can actually zoom and have a look at what the value is if I wanted to. And here, oh, this is cool. Here you can see the numerical oscillations from trapezoid integration method in Ngspice, where the current actually switches up and down a bit. Okay. I think actually also the cicsim I showed you now was the wave. Let's open that up. So that looked like this. And I've also made a newer version. And if I go to the folder where I downloaded ASEX, let's see, cd ASEX, or was it in LPro? So this was added 29th of December. So I can also, let's see, branch. So what we can see here is the current cicsim I'm running on is not the latest one. It's detached. So if I check out main, and now I can see when that was changed on the 30th. So there's some changes. I added the ability to have multiple access. Now, in order to get that installed, I actually have to rerun the install procedure. So if cicsim doesn't work, or if there's a bug, the first thing you should do is switch to head or main, and then check if that works. So if I now go in here and I type cicsim wave output tran raw, we should get a different version. Yeah, you can see that. These two are different. Well, hey. What I added in the latest one was the ability to add multiple access, so you can do things like that. And did I have the add? Well, yeah, I didn't add the ability to have log. I should have log. Yeah, or you can add that if you wanted to. It's the code's in GitHub. So anyway, let's proceed with the tutorial. All coordinate simulations. So I kind of right. So in order to do the coordinate simulations, I now have to write my typical etc mc. So etc is extreme test condition, and mc is Monte Carlo. However, I know that this is going to take quite a bit of time. So I'll just post the video while this is running. Okay, it finally finished. So I think that actually took 20 minutes to run all corners. So that's running all corners is not something that we want to do all the time. Let's actually check here. So just the corner simulations, not the corner simulation, Monte Carlo simulations took 10 minutes. And maybe it's too far up in my log to be able to see. Three, yeah, maybe not. Let's see, 2, 1. There we go. And then actually 5 minutes. Okay, so 15 minutes. But still, it's a long time to just sit there and wait. So running full corner simulations is not something that we want to do all the time. But what quite often happens is that we figure out, oh, there's something I want to measure, something I've forgotten. And that's actually possible to add afterwards. So if I go back to my tran mesh file, oh, what happened there? Tran mesh file. I want to see if the current has settled, if I've simulated long enough. So I want to extract at 9 nanoseconds. Did I really extract 10 nanoseconds? Let's check that. Yeah, 10 nanoseconds. Yeah, okay. And let's update the summary results. So my YAML file to include that one too. And what I definitely don't want to do now is run all the simulations again just to extract that single parameter. But what I can do is use this no run option. So that will not run the simulation, but run all the extractions. So that runs a lot faster and it finishes, let's see, I guess within at least a minute. So that's pretty fast. So it's really important to get used to splitting up your measurements and simulations into two parts. I've experienced with ADCs that I've had simulations running for, yeah, maybe 3-4 days. And in the old days when I started making ADCs, it was difficult to split up the measurement from the actual simulation. So then sometimes I had to rerun another 4 or 5 day simulation in order to get a new parameter. Luckily, that has gotten better. Sometimes you won't be able to figure out from the Ngspice manual. So if we open the Ngspice manual, you won't be able to figure out from the manual how to measure something. So inside the Ngspice manual, you have a bunch of commands for measure. So let's see, that's mess. There's a bunch of different things there, but maybe you don't have exactly what you need. So in order to make that a bit easier, I usually drop into Python. So cicsim also has the ability to run Python on top of your results. And all you need to do is to have a Python file that is named the same as your Spice file. So if I open the tran.py, let's see. And what we want to look at now is well, there's where we can do something. I want to delete the return file because that actually just doesn't run the scripts, and I think we're good to go. So that's the settling error, and that's the difference between the 20 microamp, which is measured at 5 nanoseconds, and at 9 nanoseconds. And then I want to add that part to my tran.yaml, and I want to run the measurements again to get all those parameters. And now it will actually also run the Python. So here you can see it skips the simulation, but it will run Python. And now we should have also the error. If we look at the top columns here, we have now the settling error in the outputs. If I want to see it a bit easier, I can do make summary. And that generates a README file, and I can use pandoc to generate something I can look at. Oh, there's nothing in there. Oh, no, wait a minute. Yes, there is. So, good thing to know is, I don't think I say it in the tutorial. Maybe I do. But there is a summary.yaml that tells the make summary what to do and where to find the simulation results. So the typical, the ETC, and the Monte Carlo. And what actually comes into the report here is going to be the results that you get. Oh, what's defined in the transcend.yaml. So let's see, what else does the tutorial want me to do? Yeah, think about the results. Right, so do we have plus minus 20%? And that's for the output current. So we can see that most of the time the output current is pretty okay. Also over corners, it's okay. It varies a bit. But over Monte Carlo, it is not within spec. So if we look at the simulation results here, we can actually see that there are a couple of corners, the Monte Carlo corner here and the Monte Carlo corner there, where the current is out of spec. And that's quite common, that you'll find that mismatch is your main problem. And for a real circuit, you would have to fix that. But this is just a demo. There is one thing I wanted to try and show you, and that is, this tutorial was written about a year ago. And since that time, as I said earlier, I've been able to simplify a bit how, or not simplify, but improve, I would say, the technology setup. So if we do a git branch, we will see that here we're running from a tag. And if I take git checkout main, now I have the latest setup. And maybe, let's see, I'm pretty sure if I run make typical, my simulation might actually, does it run? Yes, well, looks like it does. That's a good thing. That at least means my simulations are forward compatible, or my technology setup seems to be forward compatible for simulation. But what we can see in the text setup then is for Ngspice, no, for cicsim YAML. That's there should be, yeah, there should be more corners. And you can see now that we have this KFF, K, and so on. The difference between the everything, the A and the K, is the Ks are faster because they include less transistors. But for most of the simulations that we're going to do, the Ks are sufficient. Now, my simulation of the A took 30 seconds, if I go into my makefile, sim makefile here, and I change the A here to K, that's all I need to do, I think. So 30 seconds on the previous one with the K, it takes 7 seconds. So faster. And all you need to do is go in and in your makefile change the case, change the A's to K's. And your simulations should still work, but they will run about 3 times faster. Like that. Which means that our full corner run of etc should now complete in about 5 minutes instead of 15 minutes. And the only difference between them is actually how many Spice files are included. So it doesn't now include all the Spice files that you don't need. Okay, let's get back to the tutorial. So the next thing on the tutorial is draw the layout. And there I'd refer you to the video that is already there. You can watch me stumbling through the process of creating the layout. And good luck.